Hi everyone. So this video would focus on the significant property of transition metal, which is its color. Um, Now, the part that is important is the explanation that you need to give in order to justify why this transition metals complexes are able to show us color, and they're sometimes able to change into different colors when they are complexing with other or different ions. This is a very unique feature that only applies to transitional metal or the D block elements, with some uh, exceptions. Now, straight to the content. Now, it's important to identify that the ligands are one of the main culprits that is responsible to produce color. They tend to surround the metal ion, and as what you have watched in the previous video, the ligands will fill in the empty or the partially filled d orbitals to form the complex, and that produces an effect that we call as the dd splitting or d orbital splitting, which we will look at in a bit. That leads to formation of different colors. Now, let's look at this. Take note, it's the absorption of sunlight from the visible spectrum. So, as you would already know, that's basic light knowledge, that when you see visible light or the white light, it's composed of different spectrum. The objects that we see to be colored is because they are reflecting a specific spectrum while they're absorbing the other spectrum. Okay, for instance, in this picture, if you could see that the red substance here obviously absorbing all the spectrum except for red. Now, to talk about more on d orbitals, see what happens, what we call as the splitting of d orbitals. Now, once the d orbitals is filled, when the ligands come and fill in the partially empty d orbitals. In this picture, you can see all my d orbitals are empty. This leads to, in a ligand field, once it's been filled up, what they refer to as a ligand field here is essentially once the orbitals has been filled up by ligands. Now, you do not have to get into too much detail here. It's in simple term, when the ligand, okay, that's going to take a while if I were to write it like that. All right, when ligand, okay, I'm going to stop writing because that's going to take a while. This software is a little laggy because right now my laptop is also trying to convert the videos I've done previously. When ligand fills in the orbitals, it causes the orbitals to split to two different levels. You can see here, two of the orbitals takes up a much higher point and three of the orbitals takes up much lower. So you tend to always split in this order, 2 and 3. 3 remains at a lower level, whereas 2 will jump to a much higher energy level. This is due to the filling up of the ligand. Now, once it has split itself, it creates an energy gap here. So you see this is a marking of the energy gap. So that's the energy gap, and this energy gap is the reason why the color that you see is different for each ligand and each d orbitals. So essentially what happens, as best represented by this slide, once the d orbital is split in this way, this is a split d orbital, you can see that we have incoming white spectrum that has different wavelengths in it. This wavelength will excite some of the electrons from the lower d orbital, which causes it to jump to a higher d orbital. This jumping absorbs some of the spectrum that came in earlier. So some of the spectrum here will be absorbed when the electron makes its leap from here to there. And the rest that did not get absorbed tend to be released. So what you see is this, whatever that did not get absorbed when the electron jumped from the lower d orbital to the higher d orbital. Okay, so take note of that, from lower d orbital to the higher d orbital. So you can see here green-yellow light is absorbed as an electron is promoted from one set of d orbitals to the other set of d orbitals. Remember, these d orbitals were split. So this could only occur once the splitting of the orbitals has taken place, and splitting of the orbitals will only take place once the ligand has come and fill up the orbitals. So this is very, very unique feature for the transitional metals, and as you know, only transitional metals are able to complex with what we call as ligands. Okay, so blue and red light is transmitted, so what you will view is purple. This is just an example, random example for titanium complex. There are different examples. You do not need to know all the complexes that exist and what are the different colors they take, but you do need to be able to explain. The explanation for all the transitional metal colors are the same, so you just need to provide general explanation. You do not have to be specific regarding the number or what type of spectrum is being absorbed. So if I were to just summarize it for you, if the question is why transitional metals are colored, simple. Transition metals have partially filled, or you can say have empty d orbitals, which is filled by the ligand. The filling up of ligands, lone pairs from the ligands into the d orbital, causes the d orbital to be split into higher level and lower level. There's two orbitals that will sit at a higher level, there'll be two orbitals that will be at much lower in level. When visible light is shine on these orbitals, some of the spectrum is absorbed, which causes the electrons to be promoted to it from the lower d orbital to the higher d orbital. Those spectrums that is not absorbed is released as energy in the form of wavelength, and the combination of the spectrums that did not get absorbed would form the color of the particular complex. That's it. It's as simple as that. In fact, your textbook would have a much simpler explanation than that. Take note, this is just an example. Again, you do not have to talk about any particular color change, but this is just to show you how different ligands have a strength, what we call as the strength in splitting the d orbital. So we could say, just randomly pick, water sits here. We know that the cyanide is a much stronger splitting agent compared to water, and followed by hydroxyl, fluorine, chlorine, and iodine, and so on. So there's a stronger field that leads to a larger energy gap, and that produces shorter wavelength, and vice versa. So you can see the weaker field, smaller gap between the d orbitals, that means longer wavelength will be released. Okay, so that's it. That's it for this video. That's it for this learning outcome. You should be able to explain the color formation of a transitional metal complex, and these colors are explained using the concept of d orbital splitting, or also known as dd splitting. Okay, thank you very much. Have a good day.